Okay, in this problem we have steam in a piston cylinder undergoing a polytropic process where n equals 2. And it starts at initial state, given there, final state where the internal energy is at. And it says here that during the process, the heat transfer from the steam is 342.9 BTU. So that's actually a negative Q because, again, our sign convention says that heat transfer from the steam is negative. Has a mass of 1.2 pounds. It says neglecting the changes in kinetic and potential energies determine the work and then the final specific volume. So we'll start by applying our first law equation, which is the change in internal energy, delta U, plus the change in kinetic energy plus the change in potential energy equals the heat in minus the work out. Now it says we can neglect the kinetic energy and the potential energy, so we will neglect that. Okay? And what we're looking for is work. So I'm going to bring work to this side, and that's going to equal Q minus the change in energy, which is going to be my mass, times the specific energy, U2 minus U1. So that's going to equal Q, which again is negative 342.9, and it's negative because the heat transfer is from my system, which is the steam, minus 1.2 pounds times U2 minus U1, which is BTUs per pound. That will be 990.58 minus 1363.3, which is going to actually equal a work of 104 BTUs. Now that's a positive work, so that is work that my system is actually doing on the surroundings. Okay, so we use that first law, neglecting our kinetic potential energy, and basically my work is Q minus the change in internal energy. Okay. Now from this work, I can use my definition of work, which is PdV, to find the final specific volume. Okay. So again, we'll start with my work equation, which is again the integral of PdV, and I'll use the specific volume, meaning then I have to take it times the mass to go from specific volume to actual volume, so I can get to actual work here. Okay. Now, I know the relationship is polytropic, which means PV squared, n equals 2, is constant. Okay. So again, to do this integral here, I'm going to solve this for P, plug it in here, so I only have V's here. I'll have a constant that I can pull out and go from there with that. Okay, so again, my work here is going to be M times the integral. Instead of P, I'm going to use my constant divided by V squared dV. Okay, again, I can pull my constant outside of the integral. So I take M times that constant, and the constant is any state. So I'll use P1 V1 squared because I know those two values. So P1 V1 squared. That's the constant. That's going to be times the integral, again, from V1 to V2 of V to the negative 2 dV. Now I can go ahead and do that integral. The integral of negative 2 is actually going to be negative V to the negative 1. Okay, so when I do that, I get the equation for work to be M, again, times the constant, which would be P1 V1 squared. And then using my limits of integration, I get negative 1 over V2 plus 1 over V1. So that's my equation for work. Again, I know work, I know mass, I know my initial properties. All I'm looking for is V1. Okay, so through a little algebraic manipulation, I'm solving for V2, not V1. I get the following equation. So let me go ahead and write this. And then we'll actually go through the units and make sure that they all work out and you understand. Because I know I did not, on the first problem, actually go through and show you how the units work out. So I'm going to be careful, especially using English units, that we do that here. Okay, so let's go ahead and plug in what we know. Again, we're solving for V2. So again, my work is 104 BTUs. Okay. Ultimately, I'm trying to get to volume. So I need to get this now into foot-pounds. So I'm going to take that 104 times 778, and that is foot-pounds per BTU. That way I can convert from BTUs to foot-pounds, and ultimately I'm going to need things in feet so I can get them into volume. Okay, that is then going to be divided by, again, MP1V1 squared. So M is 1.2 pounds mass. P1 is 500 pounds force per square inches. Now, again, I want to get everything in cubic, or ultimately in cubic feet per pound. So I'm going to take this times 144 square inches to square feet. That will get rid of the inches. This pound force cancels with this pound force. So all I'm left with now is basically cubic feet. And I'm actually left with pounds per cubic foot. However, I'm now going to take it times V1 squared, which is going to be 1.701 squared times cubic feet, which would actually be feet to the sixth over pound mass squared, because again, I'm squaring this. But what then happens here is one of these pound mass cancels with one of those pound mass, and three of these guys cancel with that squared and that foot right there. So what I'm left with is cubic feet per pound, which is volume, which is what I'm ultimately looking here, 1 over volume minus 1 over volume. And then using, how these are buried in the denominator, I'm actually going to get it back to cubic feet per pound. Okay, so then I just subtract this by 1 over V1, which is 1.701 cubic feet per pound. Oops. Didn't quite get that right. Oh, no, I had that right. Sorry about that. That's a little messy. Apologize. All of this is under a -1. Okay. So, plugging all that into a calculator, now that I know my units are working out, I actually calculate that V2 is 3.8 cubic feet per pound mass. Now, the units are going to be a nightmare throughout the semester. Just be careful. You'll get used to it. But again, I'm converting from BTUs to foot-pounds, converting from PSI to pounds per square foot. And that basically leaves me with cubic feet per pound, which is what I'm looking for when I'm looking for specific volume. But more importantly, using my first law, I can find my work knowing my internal energies and my heat. And then once I find work, I know the relationship from work, and knowing that the polytropic process that I have here, I can go ahead and solve for the final specific volume using that relationship for work.